thinking kind of like, I want to kind of condense it down so that it's like, and don't take this the wrong way, but I want to do it as like a statistics for dummies book, right? One that is just not there to, fill your mind with all kinds of theory and things like that, but one just gives you the step-by-step process for doing all these things. So that's what we're going to try to do with these. We'll see how well we accomplish it, but I think if I do it this way, I can, number one, cover more ground and, make sure you have exposure to more things in the limited time that we have. And then number two, I can actually give you things that you can walk away with right away and use, okay? So we're going to start with some problems from 6.4, and this is being recorded, okay? So that is, that you can go back and, relive the assignment if you wish, okay? And I'll try to keep one eye on chat as we go along, but of course you can just tap your mic. It's just fine, and maybe easier if you just tap your mic and say, hey, I have a question, and then mute it. And then I can interact with you that way. We might as well take advantage of that. It's sometimes hard to ask questions in chat. So let's get rolling, all right? So we're going to do this problem right here. We're going to look at airplane seats, all right? And this is from 6.4, all right? So we're going to look at airplane seats. And airplane seats have a width of 17 inches. So we'll just go, so there are 17 inches wide. Right? Now, there's a real interesting, this brings up a real interesting question. Why does this matter? Sorry, I'm trying to create some shade here. Why does this matter? And the answer is because if your seats are wider, you get fewer people in them, right? You have fewer people that can ride your airplane. They're more comfortable. They give you better reviews on your website, but fewer people can ride them, and you make less money, right? Whereas if they're narrower, you make more money, but people hate using your airplane. So where is the break-even point, right? Where do we design our seats? And we want to be able to, the other issue is, if you make your seats too narrow, then there's a bunch of people that just can't ride your airplane anyway. Even if they love your airplane, even if you have the best snacks in the world, they can't ride it because your seats are too narrow. So, but if you make them too wide, then yeah, everybody can ride, but it's a lot of wasted space. So here we go. This airplane has seats that are 17 inches wide. Let's talk about men. Men have hip breadths, right? How wide are their hips? If I was writing this book, I'd call it butt width, right? Their butt widths are normally distributed. That's important, right? Okay, so we are, for some reason, my computer always does this. You probably just went dark. I have to restart this for some reason. About this time every day. You guys are my fourth class, so by this time. So give me a plus in chat if you're seeing the screen that I'm writing on again. Okay, great. Came back. Okay, so the hip widths are normally distributed with a mean of, this is a mean of 14.4. So the population mean is 14.4, and standard deviation, we'll squeeze it in here, standard deviation of 1.0. Okay? So here's the question, here's the type of question you're going to ask in this section. The first one, find the probability that a single individual, a single random man, randomly selected man, has a hip breadth greater than 17. Which means he wouldn't fit in the seat, right? Now, here's the deal. This problem should look familiar because this is a problem that we looked at in, I think, section 6.2. We've asked this kind of question because here, you'll remember this. The work you do is you say, okay, here's the distribution for hip breadths. And that distribution is normal with a mean of, 14.4 and a standard deviation of 1, right? Our question says, suppose you have, we want to find the probability that a single individual has a hip breadth greater than 17. So we put our boundary at 17, and we want to find the area to the right of 17. That's greater than 17, right? We've done this, okay? We've done this kind of thing, finding an area under a curve. So we know what to do. We find the z-score of the boundary, 17 minus 14.4 over 1. So that's going to be just a 3.4. Then in our table, we look up 3.40, and we get 0.9997. And that's this area, remember. That's the left area, 0.9997. And so that makes this area, which we're after, 0.0003. And that is the probability. So the probability that the hip breadth is greater than 17 is 0.0003. That's very small. That's less than 1%, right? If you move the decimal over 2, it's 0.03%, right? So that's a small probability. The other way of interpreting that answer is what percentage of men will not be able to fit in your seats? 0.03%. Or on the other side, what percent of men will be able to fit in your seats? Oh, that's the 0.9997, right? So that's a question from 6.2, right? Here's a distribution, here's a boundary, find the area to the left or the right of the boundary. Now, what changes in 6.4 is now we don't take a single person. We don't just take one person and ask what the probability is that they fit in a certain range. What we do is we take a sample. We take several men. Okay, so let me show you what I mean. So let's do this. Let's consider a sample of n equals let's use 16 men. Okay. So we're taking 16 men, and then we're going to find their average weight, the average of these 16, and we're going to ask this question. What is the probability that the average or the mean of these 16 men is greater than 15? Okay. What is the probability that it is greater than 15? Okay. Now, and hopefully you've watched all the videos from section 6.4, right? This is something you should have done. So this hopefully is just a review. Well, what's the probability that the average of these 16 men is greater than 15? Well, now all of a sudden, since we're not talking about individual men, we're talking about samples of size 16, we're talking about the sampling distribution. And we've learned that sampling distributions are normal. And so this is not the distribution of individual men. This is the distribution of sample means from samples of size n equals 16. It's still normal, so it doesn't look any different. But what is different here is the mean of this is, first of all, called the mean of the means, because this is a distribution of means, not of individual data points. So the mean of the means is the same as the mean of the population, right? So here's the mean of the population up here, and look, the mean of the means is the same. So that's nice. What changes, though, is that the standard deviation of the means is actually the standard deviation divided by square root of n. So we're using a new standard deviation. And we've got this nice, neat little formula, which says we take the original standard deviation, which was 1, right there, or right there, right? And we divide that by whatever the sample size, square root of the sample size, or square root of 16, so that's 1 over 4, or 0.25. See? So, once we have that new standard deviation, the gain is the same. What was the original question? What is the probability that the mean of these 16 men is greater than 15? So that's telling me put your boundary right here at 15. And we want greater than that. Bam. We want that area. So I just need that area under the curve. So how do I do it? I find the z-score of my boundary, just like before. So it's going to be 15 minus 14.4. Now I use my new formula, 0.25. Right? And so what you're seeing here is that we have a slightly different z-score when we're finding z-scores for sampling distributions of sample means. There's the x bar minus the mean of the means, this is what the notation looks like, over sigma over square root of n. And if you watch the videos that I posted for section 6.4, you'll see this language and notation used. Okay? But that's the formula that you use in these cases. All right, so let's continue this. Let's figure out what this z-score is. So I'm throwing in my calculator. 15 minus 14.4 divided by 0.25. Okay, is 2.4. And so that's the z-score, 2.4 of that boundary. So I want to find the area. I look it up in my table, 2.40. And I get 0.9918, and I got to remember, 0.9918 is this side, so that makes this side 0.0082. That's the area I want. So the probability that the mean is greater than 15 is 0.0082. And so I did a whole discussion on those things. But okay, so there's a reason we do this, these two problems together. Even though this first problem that we did was from section 6.2, right? The reason we did it is, number one, so that you could see that the procedure is pretty much the same. You're finding an area under a normal curve, right? Number two, the reason we do it is because you need to be able to distinguish when you're dealing which method to use. Okay, the two methods are, in the first case, the situation where we just choose a single random person. In which case your z-score formula is just as always. Z equals x minus mu over sigma, right? And in the second case is when we take a sample of a certain size and we ask about a probability, in which case your formula is right there. But other than that, the methods are the same. You put in a boundary, you find the z-score of the boundary using either the appropriate formula, one or the other, and then you just use the same table to find the area. Okay? So you'll see this, if you go back and look at the example problems, you'll see this worked out several times for several different examples. And then if you watch you probably all noticed that I'm working through kind of short lectures on the PowerPoint slides because I still want you to have some information with those. But those are available as well. All right. Give me a plus, minus, or equal in the chat if that makes sense. Pluses, minuses, or equals in the chat, would you? Okay. All right. So again, you've got several examples. All right. I'm going to continue here because I want you to see something from 7.1, and probably won't get to 7.2, even though that's going to pop up on your radars right about the same time 7.1 does. Okay. Let's take a look here. Okay, so 7.1, new topic, new chapter. There will be a chapter 6 test, so watch for that as soon as I get that posted. But I want to look at 7.1. Okay? And 7.1 is entitled this, Estimating a Population Proportion. All right, so let me give you an example. Suppose I want to know how many people have internet at home. Okay? How many adults have internet at home? And I would love to know what the percentage is. That's a proportion, right? What the percentage is of people that have internet at home, so that when we have a virus outbreak, I know how many people are going to have access to the internet. So this is an important question, right? But there's no way I can go out and survey everybody, right? I can never find this. This population proportion is unknown to me at this time and impossible for me to find. So I'm going to try to estimate it. There are two ways that I can estimate it. They both start with the same thing, and that thing that they start with is we're going to go out and find a sample. So the way we're going to so let's write down a problem. Estimate the total proportion. I won't say total. That makes no sense. Just estimate the proportion of people with internet at home, right? I'm going to just leave it like that. Okay. So the way we do this, and you've taken enough statistics to know that what we're going to do is we're going to work with a sample. Okay? So we're going to go out and maybe we sample 100 people. And out of those people, we get X equals 62. These are the people with internet. So that means 62 out of 100, or 0.62, right? 62%. That's what we call p-hat. Okay, p-hat is the proportion that we get from the sample. All right? I should mention this. We're estimating the population proportion. We use p, just plain old p, to be the symbol. We're trying to estimate p. Well, we found p-hat to be 62%. So one way to do this is just to use what's called a point estimate. Of p. All right? And the real simple thing is this. This is simply this. Use p-hat to estimate p. I.e., based on our studies, p, this unknown value, right? P is going to be approximately 0.62. Where did the 62 come from? From our sample. So we simply just plug in the value from the sample and say, that must be the population. Okay? But if you go back and if you go and watch the discussion about these things that I've posted, there's a bit of a problem with that. I mean, that's really specific, right? We've only surveyed 100 people, and from that, we're just going to, boom, just say, oh, 62% of all adults have the internet, right? Well, that's not the way it works, right? I mean, that's a point estimate, but it seems way too specific. And we know that we only surveyed 100 people, so we feel like we're not really being intellectually honest. But that's one way to estimate P. The other way, and this is the way that we're going to use and gets used most often, is called a confidence interval estimate. And so basically what this is going to do is this is a way to not just give, say, P is 62%. What we're going to do is we're going to say P is between 57 and 63% or 65%, right? We're going to give a range, an interval from 57 to 63, or from 55 to 71, right? So you give an interval, and that seems like a little safer bet, right? I'm not claiming that 62% of all adults have the internet. Instead, I'm going to say something like, between 57 and 67 have the internet, right? So that gives us a little fudge room, a little wiggle room, given the fact that we're working with this sample. So let me show you how to create this confidence interval. The first thing you do is you determine how confident you want to be, your level of confidence, right? And the problem is that you'll be doing this on in the homework. We'll tell you what level to work with, okay? So you don't determine this on your own. It's given to you. If you're in the real world and you're doing research, you just decide. And there are several confidence levels that are typical, usually 90%, 95%, or 99%, right? And these are just what they say they are. If I say I'm 99% confident, that means I'm pretty close to certain, right? As opposed to if I say 90% confident, that's still pretty good. I'm 90% confident that this is correct, but it's not 99% confident. I decide what level I want to be. Now, here's the trade-off. The more confident I am, the wider the interval is going to be, right? So I'm 99% confident that the true proportion is between 40 and 80%. Great. You're 99% confident. That seems like you're pretty sure that you're right, and that's good. But the problem is your interval is so wide that it's almost not useful. 40 to 80%, that's a big range, right? So the more your confidence level goes up, the higher your confidence level, the wider your interval. So it's always this trade-off, and the wider your interval, right, the less accurate you're going to be, or less specific. So it's always this trade-off, how confident you want to be versus how specific. Now, that works in reverse. If you give a very small, narrow interval, right, great, you're specific, right? If you say your interval is between 61 and 63, boy, that's pretty specific. But you may not be very confident that the true value is between 61 and 63. So it's going to be a trade-off. The more confident you are, the wider your interval is going to be. The less confident the narrower your interval is going to be, which is good, but the less confidence you're going to have. So anyway, determine the level of confidence, and let's suppose we want to be just 90%. So in our case, we're going to do 90%. Okay? Now, here's the deal. You're going to construct your confidence interval. Using this formula. You start with p hats, bam, and then you're going to add or subtract an error, and that's going to give you your low level when you subtract the error, and your upper boundary for the interval when you add the error. Okay? So in our case, that looks like this, right? P hat was 0.62, so we got from our sample. So we always start with the sample, and then we're going to add or subtract the error. What you now need is your formula for the error. Okay, so the formula looks like this. It's going to be a z-score times the square root of p hat, that's our sample. Q hat is 1 minus p hat over n. And that's your formula. If you can calculate E, then you plug it right in here and you've got your confidence. Now, let's work through this. Z is the first thing we need. Z depends on how confident you're going to be. Okay? And write this down. The Z's you want are found on the bottom of table A2. Okay? If you go back and watch some of the other lectures that I've posted, or watch the other lectures in my stat lab, they'll show you how to use it. But look on the bottom of page 2, or the bottom of table A2, and you see your various confidence intervals and associated critical values. That's what we're talking about. Z is a critical value. So for confidence level of 90%, the critical value we want is 1.645. So that goes in the table there. And then we continue here. P hat is 0.62 times Q hat is 0.38, just 1 minus P hat, over N, that was 100. Okay, so we're going to throw this in our calculator, and we're going to see what it spits out. All right, so give me 1 second. And we get 0.07. Let's round to 3 decimal. If we round to 3 decimal places, that's good. 0.080. It was like 0.0798. Okay, so here's how you use this. Your confidence interval. So now you've got 0.62 plus or minus 0.080. Where did I get the 0.38? Q hat is 1 minus P hat. Hopefully you're seeing my screen. Q hat equals 1 minus P hat. Just give me pluses in chat if you can see my screen. And that's where the 0.38 came from. 1 minus 0.62. Okay. All right. Now, so I've got my plus or minus error. So that means I'm going to subtract it. If I subtract it, it gives me 0.54. If I add it, it gives me 0.70. There's my interval. P is somewhere between those. And so that's the 90% confidence interval. And so when I report this, I want to write not only the interval, but I want to say that this is my 90% confidence interval. Okay? Because I need to tell them how confident that I am. And when I write that, that means I'm 90% confident that the true proportion of people that have internet is between 54% and 70%. Okay? And that's how you create the confidence interval. It boils down to finding your P hat from your sample, calculating your error using this formula, and that's your confidence interval. Okay. Now, I'm going to throw in some information on 7.2 real quickly. And because 7.2 is finding the confidence interval estimate for, actually I won't do that. I'll create a separate video for that. But you'll notice we're doing the same thing. We'll just be using a different error formula. Okay, you'll see that in the next video. Okay, we do have a little bit of time. Well, we don't have much time, but we have just a little bit of time. Do you have some questions? Is there anything that I can help you with on this particular topic here? Remember, this is 6.4, 7.1, and 7.2 are what you're scheduled to start today. So, you know, if you're not up to that point, you got to catch up to that point. Watch the videos, work the homework. We'll get all that posted for you today. In addition to finishing up your chapter 4 and 5 tests, which hopefully you already did because you've had some time with it. Any questions? There's plenty of these examples that will show up in the example videos. Yeah, so go back and watch this one, Brenda, and then watch the other examples that I've worked out. Right, this is your first time seeing it, so it'll be a little new to you. But I would watch the other ones. And then if you guys are seeing questions or having questions, send me questions in Canvas. Okay. All right. I hope you guys are doing good out there. You got to let me know. You got to give me feedback. We've talked, I think, about the fact that you can get tutoring on this and get other assistance and help. These examples that we did, this thing today is recorded. Yeah, you'll find it if you go to the online module, you'll see it posted eventually under I think I'm referring to these live sections as tutorial sessions. So that's where I'll be posting. But I've also worked out some other examples in the examples section as well. Okay. Okay, guys, that's all we got for you today. So go have a good, safe day. Again, let me know if you have questions, and